Okay, hello and welcome to Lecture 3C Differential Control. Today we'll be learning about what is differential control, how to use it, and the goods and bads with differential control. Okay, what does differential control look like? Well, it looks like this. KD multiplied by DE over DT. So what is KD? Well, KD is a differential parameter. Differential parameter. Remember, this is tunable, so we are tuning it. And it's just a number, so could be 1, could be number, can't spell that wrong, can I? Number. Okay, number could be any little decimal, 0.2, 1, 1 million, anything. Okay, DE is the rate of the error. So all that stuff is here, all the rate of the error. Anyone who's not too familiar with differentiation, part of calculus, differentiation is finding the gradient of a signal. So the gradient is how steep. So it's looking at how steep is the error. So if I draw you a little graph, that's my graph, and you have this blue signal. So here we can see that this part here, very steep, so that's very steep. And this part here is obviously flatter, so less steep. So what's actually happening here? So what KD multiplied by DE over DT is, or this stuff here, well, that is controlling the rate of the output. So if the rate is very, very steep, we are trying to slow it down. So let's write that down. So controlling how steep the output is. If the system is trying to rise too fast, differential control will slow it down. It slows down the output. And this is very important because if your system is rising very, very fast, like it's overshooting, differential control will do its best to slow down. It's good for removing overshoots. So removing overshoot. And it's also good at reducing oscillations. Reduces oscillations. So from all of this, what we understand with differential control is it smooths down the signal. So the main point to understand with differential control, it smooths down the signal. So let's draw something else, clear this up. So remember, it smooths it down. Output signal. So let's look at this with a graph. Here's a graph of some motor speed. So, well, that's time, of course. This is speed. Now, if you have a motor that is rising really, really fast, what's happening with differential control is differential control sees that perhaps is too fast, or the gradient is too steep gradient. So by applying a KD parameter, so by tuning and increasing the KD parameter, we are actually saying if it's too steep, slow it down. So by increasing KD, we are scaling the rate of the error. The rate or the steepness of the error, or of the output signal. And by increasing KD, we are scaling the rate, which means we want to smoothen out the signal more. So by increasing KD, we are actually smoothing the signal out more. We smoothen signal out. So because KD has been applied, I'll draw that in orange. We look at that and say, well, actually that is too steep. So what KD does is it smooths it out. Now, of course, it's good at removing the oscillations too. And that's typically how KD would work. Now, of course, that line is not exactly what it would look like. It's a bit high up, but the point of KD is it removes this oscillation, it removes the overshoot, Ooh, I could spell better. Why does it remove the overshoot? Because the gradient of the overshoot is typically very steep or high gradient, very fast change, and therefore it gets removed. Oscillations typically get removed too. And why are oscillations removed? Because the gradient is too high. And so by increasing KD, we are reducing and smoothing down the signal, which reduces the overshoots and reduces the oscillation. However, this means that your system slows down. So the main point to understand here, it is anything, differential control slows down a system. It slows down a system. If there's anything you should remember, it slows down the system. And remember that we discussed in the second lecture, that slowing down a system means you have a less overshoot. Slowing down a system and having less overshoot means you have less oscillations. So that's the main point to understand, is it slows down the system. Sometimes in control textbooks they call it damping. So I could say damping. That should be a D. Damping. So that's what damping is. It's slowing down the system. Okay, now it's important to understand with differential control that it amplifies the rate of the error. So KD amplifies the rate of error. Now, this is good in situations where you want to slow down, say, a motor or something. But this is actually really bad in high frequency noise situations. So if I draw a graph, and imagine this blue signal is whatever device we are using here. Now, the problem with this is, imagine this is high frequency noise. Now, high frequency noise meaning it's very steep. High frequency noise. What does KD do here? Well, KD actually amplifies the high frequency noise, and that causes a lot of instabilities and oscillations. It thinks it's trying to smooth it out, but in reality it amplifies this noise. So what you get instead is, well, it'll smoothen that part because that's alright, and then it will just oscillate. And you will not really know why that oscillation happens, but when you test your system, you need to be careful with KD, because increasing KD too much, or having KD to begin with, amplifies high frequency noise. So avoid using KD where you have high frequency noise. So key point, avoid KD where there is high frequency noise. Let's just rub that out and put it in a nicer location. There is high frequency noise. Be very careful with KD. It amplifies the noise that can cause instability, and your system will act erratically. How to use it? So make KD large enough. Make KD, or add KD. Make KD large enough to smoothen out oscillations and slow down or dampen overshoot and dampen system. But be very careful with KD if you have high frequency noise, because it acts very erratically to high frequency noise or steep little changes. So, but be careful when you have high frequency noise. And if you do have high frequency noise, try to filter it out. And if you can't filter it out, then just avoid KD in general. The goods. So what's good about it? It smoothens the system. It also reduces oscillations, which is basically smoothing the system. It's also good because it reduces overshoot. So a good part of differential is it's keeping track over the rate of change in error. So it keeps track of a rate of change of error. Okay, so what are the bads about KD or differential control? So it's very unstable in high frequency noise. Very unstable in high frequency noise. C, noise. Remember that KD is amplifying the rates of change of error. So if it's high frequency noise, that's a high rate of change of the error, which means KD is amplifying that and reacting way too strongly to it. So this typically causes jittering, oscillations, and other crap. And it's not good for systems with high frequency noise. Another major problem with differential, which I haven't talked about, is it's very hard to tune, very tricky to tune. In fact, it's the hardest out of PID to tune because you have to test your system in noisy environments, or if an unexpected situation happens, very, very tricky to tune it. Okay, to summarize, we saw that differential control is used to control the rate of the output signal. It does this by amplifying the rate of change of the error. So remember, that's supposed to be a star, by the way. Amplifies the rate of change of the error. And by doing this, it actually smoothens out a signal, or it dampens it. Dampens the output. Be aware that this slows down your system. Now, you must be really careful with KD or differential control because it causes instability when noise is high frequency or has a very steep gradient. Thank you. My favorite part, the end. Next lecture. Lecture 3D, all the PID parameters together. So that's PID all together in one. Hope to see you next time. Bye.